watching the video. This is the third one and the final one that is designed to cover the remaining topics of Chapter 7. Tomorrow in class, we'll go over section 8.1 and 8.2, focusing on some spatial graphs. And then finally on Thursday, section 8.3, which will be the final section of the semester. I will go over a couple of other directions tomorrow in class and then a couple announcements as we are finalizing this week the semester with the last two remaining classes. And then, of course, the final exam next week scheduled for Thursday, December the 12th, scheduled for Thursday, December the 12th from noon 12 to 2. Pay attention, the final exam time is different from the regular class time. Our regular class starts at 12:45 and ends at 2:30. The exam time has a shift starting at noon, starting at 12, ending at 2. So if for any reason you are going to totally forget about the time, which again, I will continue to remind you. And then if you're using a regular calendar or some way of reminding yourself, make sure to write the exam time that is, and write a note for yourself that is different from the regular class time. But let's say you're showing up at 12:45, you only have 1 hour and 15 minutes remaining to take the exam. The exam is 2 hours with no possible extension. Okay, so let's get started. I'm gonna go ahead and then share the screen. And then I'll go directly to section 7. 7.3. So we went over the adjacencies, the adjacency list, the matrices in our second video. And then this is where I stopped. We looked at these three conditions of the graphs being isomorphic. I explained in the previous video, the isomorphic comes from the word iso, meaning the same, and morph, meaning the shape. So two shapes that are the same. We have these three conditions. Graphs G1 and G2 are isomorphics if and only if the three conditions are met or satisfied. Both graphs are sharing an exact number of vertices and an exact number of edges. So the same number of vertices and edges. Both graphs have an equal sequence or the same sequence of the degrees. And then every vertex in G1 corresponds to a vertex in G2 such that both adjacencies or both the list of adjacencies or the matrix of adjacencies, if you want to call it. I mean, you can use whatever you think is the convenient. The matrices are always, if there is an edge connecting two vertices, you write 1. If there's no direct edge connecting two vertices, you write 0. This is how the matrix is created. Or you create the table of the adjacencies for each vertex that has a direct edge connected to other vertices of the graph. So we went over this example 1. This was a typical case where condition number 2 failed, was not satisfied, therefore the graphs were not isomorphic. Now let's look at another case. This is where I stopped in the previous video. So now we're going to look at this particular case where we're trying to show that both graph G1 and G2 are isomorphic using the three conditions. So the way we do this, we start by going over the conditions. Let's see what the graphs are. This is graph G1. Pay attention to the vertices. So we have A, B, C, D, E, F, G. For G1, now these are the vertices of graph G2. Later on, I'm going to rename these lowercase vertices of G2 in the way that it's going to allow me to compare the list of adjacencies for both of them. But for now, let's start with how many vertices are in G1, how many vertices are in G2. If I count, I have A, B, C, D, 4 at the top and 3 at the bottom. I have 7 vertices. And now let's look at 1, 2, 3, 4, 5, 6, 7. So I have 7 vertices of G2. So the number of vertices for G1 is 7. The number of vertices for G2 is 7. So they share the same number of vertices. Now let's count the edges. So A to E is 1. So A to B is 2. B to F is 3. B to C is 4. C to G is 5. And C to D is 6. So the number of edges for G1 is 6. Now let's see if this is the case for graph G2. H to I is 1 edge. N to J is 2. J to L is 3. M to K is 4. J to K is 5. And K to I is 6. So these two graphs share the same number of vertices, the same number of edges. Therefore, condition number 1 is satisfied. Now we are going to test the sequence of the degrees. Let's start with the sequence of degrees for all the vertices of graph G1, A, B, C, D, E, F, G. Vertex A has a degree 2. Why? Because it has a direct connection with 2 edges from A to E and from A to B. Now vertex B has 3, degree 3, because it's connected to A, to F directly, and to C. Vertex C has a degree 3 also. It's connected to B, to G, and D. Vertex D has only one edge directly connected to C, so degree is 1. Vertex E also has a degree 1. Vertex F also have a degree 1. And then vertex G also have a degree 1 because they're only connected by one vertex with a direct edge. So the sequence of the degrees in this case starts with a 2. Then, so we have 1, 1, 1 for 4 vertices, and then a 2, and then a 3, and a 3, if I place them in order. Now let's look at the second one, the second graph. I start off with H, so just one edge. H is the vertex H. It's connected to I only, so degree is 1. Now, another vertex that has only one connection is N. Another vertex that has only one connection is M. And then another vertex that has only one connection is L. So these are all 1, 1, 1, 4 of them. Now, a vertex with 2 connections is I. So this is the same as vertex A. That's going to help me out. These degrees are going to help me out when I rename the vertices of G, trying to match them with the graph G2, trying to match it with graph G1. So these H, N, M, L are the E, F, G, and the D, E, F, G, right? So these are all 1, degree of 1. I is the same as A. And then now J and K are the same as B and C because J has 3 connection and K does have 3. So the sequences of the degrees are going to be 1, 1, 1, 1, 2, and then 3, 3. So the sequences are the same. Condition number 2 is check is satisfied. Now let's transition to condition number 3. I'm not creating a matrix. I'm going to create a table of adjacencies for each graph. So I know that A is connected to B and T because the degree is 2. So A is connected to B and E. B is the one with degree 3. It's connected to A, to C, and F. It's connected to A, to C, and F. B is connected to A, to C, and F. C is connected to B, G, and D. B, D, G. Yep. And then we have these 4 vertices, D, E, F, G, that are connected to only one. So D is connected to C, E is connected to A, F is connected to B, and G is connected to C. Now we're going to try to use the same vertices. So name them A, B, C, D based on their connection. Remember when I showed you in the previous graph, this vertex right there with the 2 degree 2, so 2 direct connection, 2 edges connected. This is the same as your A. This is the same as your A. And then the B and C are the degree 3 with 3 connections. These are going to be the J and the K. So one of them is B, the other one is C. And this H, N, M, and then L. So all of them are going to be the E, F, G, and D. So if I follow that idea, then I should be able to rename the vertices of the second graph to make it easier for me to compare the tables. So as I say, the I becomes an A. This is E because it's one connection. This is the H, right? The B and the C are the ones with the 3, and then the rest of them are D, F, and G. So if I do that, then I start looking at the table. A has a connection to E and B. B has a connection to A, C, and F. C has a connection to B, D, and H. D is connected to C, F is connected to B, G is connected to C, and E is connected to A. So therefore, the two graphs share the same adjacency tables, so they are condition number 3 satisfied, which exactly means that the graphs are isomorphic. And from the isomorphism of the graphs, we transition to another example of the graph, the planar graph. Now, what is special about the planar graph? We are going to see a typical example that allows us to understand the idea behind the planar graph. But a graph drawn with edges crossing in the plane that cannot be redrawn without any edges crossing is called a planar graph. Now, when you look at this definition, it's kind of like very difficult to comprehend it and then understand, and it makes it very difficult to even say the definition. So with my next example, I'm going to stick with the definition, and then as I go through the example, I will make sure to give you to create an opportunity for all of you to understand this kind of like complicated definition of planar graph. So I start with this particular graph right there. And then you see the two edges are crossing. So we have a graph that is drawn with two edges that are crossing. It's very obvious that the two edges are crossing. Now, this is first part of the definition. So you have a graph where the two edges of it are crossing. Now, you are going to make an attempt to redraw this graph. When we redraw the graph, the crossing between the two edges will be eliminated. That's the idea behind it. If we successfully eliminate the crossing without eliminating any of the vertices, then the graph automatically no longer has the crossing of the edges and becomes a planar graph. If this can successfully be eliminated and then you redraw successfully without the crossing being present, then the graph automatically becomes a planar graph. And there's a nice property that the planar graphs satisfy. This is not always possible, but if it is possible, then the graph becomes a planar graph. So this is what I'm going to do. I'm going to consider this top vertex, which I'm going to call it A, and you see it in the next image. Now, this is the edge, which is dashed, means that I'm about to eliminate it or remove it. This is the curve that I have to redraw, and this is the other edge that has to be removed. No, has to be redrawn in the way that allows us to create the planar graph. So redraw the two edges, do not remove them. Redraw the two edges, and then the loop, do not eliminate them. Now, the notation dashed means that they are going to be placed somewhere else, but they're not going to be removed. So the way I do this, I'm going to take this top vertex A and flip it on the other side of this edge, on the other side of this edge. So this is the flipping on the other side of this edge. So I'm making them thicker so you can see what's going on. So once I move A to the other side of it, this is going to be connected to this vertex, but not by this crossing edge. So this is the connection. And connected to this vertex again, connected to this vertex again. So the two dashed edges now are the thick ones, or the solid thick ones. And then the loop is a connection between this existing vertex and an A that is flipped on the other side. So this is the new image after we flip A from the top to the bottom on the other side of this edge. If I call this the diagonal edge. And then if I successfully do this, which I did it for this graph, this new graph is going to be called a planar graph. And then it is a connected graph. And then a connected graph that is in the category of planar graph, with V being the vertices and E being the edges, satisfies this condition. E, the number of edges, is less than or equal to 3 times the number of vertices minus 6. So if this condition is satisfied, the graph is planar, otherwise it's not. So now let's look at an example that is a direct application of this. Show that the graph below is not a planar graph. So this particular graph is not planar. So what I'm going to do is I'm going to rely on that number of edges and number of vertices idea, so then I can test the inequality that the previous theorem is giving us, where E, the number of edges, must be less than or equal to 3 times the number of vertices V minus 6. So how do I do that? I start off by finding the number of edges. There's a theorem that allows us to find the number of edges if we do know the degrees of each vertex of the connected graph. So the degrees are determined by the number of edges that are directly connected to the other vertices. So this vertex has a connection of 1, 2, 3, 4, 5. So that's degree 5. This one has a connection 1, 2, and 3. So that's degree 3. Now we have 1, 2, 3, 4, 5, degree 5. This one right there looks like inside internally. It's 1, 2, 3, and 4. This one has also 4. And then the final one has 5. Now that I know the degrees, the next step is I get the total number of the degrees by adding them up. So I have 5 plus 5 plus 3 plus 5 plus 4 plus 4. So the degree total is 26. Now, why do I need the degree total? By one of the previous theorems, direct theorem, we know that the number of edges is the half of the total number of the degrees. So if the total number of the degrees is 26, if I divide it by 2, this particular graph has 13 edges, and that's the best way to find the number of edges. I mean, you can, as I mentioned in section 7.2, and you can watch the video recording of it, you can still count them. But if you rely on counting, more likely either count one of the edges more than once, that's a higher chance of doing it, or higher chance of missing any of them. Now, this particular formula where you use the total number of the degrees divided by 2 to get the number of edges is the one that I will encourage you to use it to get the exact number of edges. So we do have 13 edges. Now we are going to test the inequality to see if it is true. If it happens to be false, then this is not a planar graph. This is better than kind of like taking the idea of redrawing, which I did it, and then can be done for a smaller number of vertices. It gets complicated when you increase the number of vertices, and then the connected graph is way too complicated. So we are testing the inequality. E less than or equal to 3V minus 6. If this is true, then the graph is planar. If this is false, the graph is not planar. We have 13 edges, so I'm going to place 13 on the left-hand side. And then we have 6 vertices. If you count them, these dot signs are the vertices. So 1, 2, 3, 4, 5, 6. Do not get confused with the degrees and the number of vertices. Degrees are different. You count the degree for each vertex, you add them up to get the total degree. Now, the dots that are connected to create the connected graph are the vertices of the graph. So we have 6. So let me plug in on the left-hand side, on the right-hand side. So on the left-hand side, we have 13. On the right-hand side, we have 3 times the number of vertices. So 3 times 6 minus 6. So that's 18 minus 6, which is 12. And then we do know that 13 is not equal to 12. 13 is not less than 12. So this is a false statement. This statement is true if one of them is true. It's either less than or equal to, which is not the case. So therefore, the above graph that you see in there, it is a connected graph, but unfortunately, it is not a planar graph. And that particular theorem, it's, as I said, widely used compared to redrawing the graph in order to create a planar graph from a given connected graph where 2 vertices are crossing each other. So that's all for section 7.3. This is the end of 7.3. And now I'm going to transition into an important section, which is the last one of chapter 7. And the idea that is behind this particular section, it's again related to the connected graph. So it uses the idea of connected graph, but it is giving us a spatial algorithm, which is pretty much what you learn as part of this section, a spatial algorithm that is allowing us to use the connected graph, but at the same time going from an initial vertex to the other one, to the vertex Z, so creating a path from one vertex to another, not a circuit. This is true for paths. From one vertex to the other, let's say from an A to Z, I've been able to identify the shortest path possible with the lowest possible cost. This is extremely popular when you're traveling and you're trying to, it's the idea behind the well-known GPS, which gives you the best option, the shortest path to go from one destination to the other with the lowest possible cost in some scenarios. So that particular idea is behind this graph, where you're not only going to see a connected graph, but in addition to it, you are going to see some weight that goes along with the graph. Now, what we weight, and then the weight kind of like represent the cost. This is how we refer to. We are weighting the edges of the graph. And then based on the weight of the edges of the graph, this is how we determine the shortest path. Now, the connected graph that you are about to see, because this particular algorithm, if you treat it as a general case, it's going to be way too complicated. I mean, even with a spatial example case, it's complicated. You have to get the idea, at least you have to go over twice the same example in order to understand the idea behind it. So as you are going to see, and I'm about to share with you in a minute, we're going to rely on example to explain this, but you are going to see a connected graph, and then the vertices of the graph, of course, the edges. But then what are you going to see as a new element? All the graphs are including numbers along the edges. And then these numbers along the edges are indicating the weight associated with using each of the edges. And then the reason why we do that, because the weights are going to allow us to determine the shortest path. This particular algorithm is created for the first time by a Dutch mathematician, a computer scientist, not mathematician. His first name, Edsger, this is how you pronounce it, and then the last name, Dijkstra. The Dijkstra algorithm, this is how we refer to the Dijkstra algorithm, is well known in the computer science, and then it is an algorithm that is, as I said, widely used in the process of navigating or traveling from one place to the other. To understand the Dijkstra algorithm, we are going to rely, as I said, on one example. The algorithm also keeps track of the cheapest path to visit anytime we move from each vertex to the other. If we are going to moving from one vertex to the other, we get a path that is the cheapest, and then later on we find another one that is cheaper than the one that we computed. We backtrack, we cross out that particular path, and then add the new one. So the idea behind it, as we go from one visit, we call them visits, to the other, is to visit all the vertices. In some scenarios, we have to backtrack because we are going to be able to find a shortest path of the one that we generated previously. But the general idea behind it is at the end, when we move from one location to the other, the goal is to get the shortest possible path to go from vertex A to vertex C. And here is the example. Now, as you see this image, you notice that we have vertices A, B, C, D, E, F, and Z. We are traveling from A to Z. We're going to use the Dijkstra algorithm to find the shortest path from A to Z in this graph below. Notice that you have numbers. These are the weights. So the age from A to C has a weight 6. The age from A to B has a weight 3. The age from B to C has the weight 2, and so forth. So the numbers are representing the cost or the weight. So how do I start? You rely on what we call the visits as you transition from one vertex to the other. Now, the first vertex that we do not include in the table representing the visits, it's going to be the vertex A because that's our starting point. So the visits are going to create a table, which we refer to as the visit list or the table list. The part of the table, it's going to be a column representing the vertex, and then a column representing the labels. Now, these labels in some scenarios are going to be defined by a single number, which is the weight of that particular age as you move from one vertex to the other, or possibly the outcome of summing up the weights of maybe 2 or more than 2 ages. So let's try to look at the first step. So the first visit, I'm going to call it visit A. So we start at A. Therefore, in the visited list, which is the table or the visited table, under the vertices, we do not include A. This is your starting point. So we include all the remaining vertices, B, C, D, E, F, Z. Now, what's the label? Initially, I'm not moving anywhere. I'm at A. So that's why A is boxed or circled, if you want to call it. So therefore, I'm going to give them the maximum weight. This is the weight, not the current weight that you see in the graph. This is the weight that you determine as you move from one to the other, or in more than one vertices, if that allows you, in more than one vertex, if that allows you. So we are going to start with all of them, except A, being labeled as infinity. Infinity is the idea of this is the maximum label of the paths, okay? And then we are adjusting. So that means we're going to cross out these infinities, which is at most you give them, and then replace them by actual numerical values that are going to determine the shortest possible path that transitions us from A to B to C and so forth. So now we start moving. We are going to move from vertex A to B and then update the label of B, right? If I go back to the graph, I notice that from A, I can move to B, and then I can move to C, all right? So that means I'm going to reach vertex B and C from vertex A. And then circle B, cross out, I'm going to circle B, I'm going to cross out the infinity sign, and then replace this by the actual weight. If I move from A to B, the actual weight is 3. So how do I write this? Let's transition into the next step. So this is visited list A and B. So I just left A and then went to B, right? So I circled B. I crossed out the infinity, and then this is 3 from A, right? So 3 represents how many what is the weight or what is the cost of traveling from A to B. But notice that I can also travel from A directly to C with a weight 6. So that means I'm going to say C, cross out the infinity, put the 6, which is the current weight between A and C. So 6 units from A. So that means B is updated. It is visited. I won't be able to do anything about B. It's going to stay as 3, labeled at 3. But then I see opportunity to update C. So that's why I'm not circling C. So let's go back to the image. There are 2 paths to go to C. One is the direct from A to C, which is 6 units. And there is this interesting path. So I can go to B first with 3 units and go to C, which is 2 units. And then this is cheaper than going directly from A to C. So remember the idea of the buses and the bus routes that I showed you? Traveling from New York to Baltimore, from Boston to Baltimore. You can go directly from Boston to city to Baltimore city, or you can take a route going to New York first and going to Baltimore. So you have to choose the cheapest. The cheapest in this case is going to B and then going to C. So I reach this C from A and B. This is how we read it, which is cheaper because it's 3 plus 2, 5 units. So then I'm ready to circle C because I reached C. There's no other option for me to go to C. So that means I reached C. I circle C. I circle C. I'm going to cross out 6, but I'm going to cross out infinity, cross out 6A as well, which I forgot to cross it out. And then now I have a different route, which is through A and B, 5 units. So now I have to go to D. How do I get to D? In order to get to D, let's go back to the image. Currently, I have infinity. So we are going from A to B 3 units, from A to C using the route A, B, C 5 units. Now I have to go to D. One option is this where we are, we reach C, right? So after reaching C, then I can go from C to D, which is 6 plus 4, 10. That is one option. Or I can do A, B, and then D, and that's 6 units. So therefore, it's better path. So I'm going to update D as 3 plus 3 with 6. So I reach D from A and B. So let's go back. So I reached D. I reached D from A and B. So I crossed out the infinity. D is reached from A and B. I did not use the other path. Why? Because it's more expensive. So if I do A to C, I already deleted that. By the way, I already, even if I wish to, I won't be able to because I already deleted this path. I decided to go to A, B, and then C. So reaching C from A and B. I'm reaching D from A and B as well. So now we have to consider E, F, and Z. We just reached D, and there's no other path that is going to give me the shortcut. So therefore, here we are at D. So now I have this visited list A, B, C, D, and let's transition to the vertex E. Before I get to vertex E, let's see what are the options for E. How do I get to E? So if I'm reaching the vertex E, so let's go back. Here's where E is, right? So I can reach vertex E from C. Remember, I decided to eliminate this path directly from A to C, so I cannot use 6. So I have to go A, B to C, which is 5, plus 4, 9. So I can reach E if I go A, B, C. So that's why you see in this table, I'm reaching E, 9, A, B, C. So I'm using A, B, C route, 9 units. A to B to C to E, 9 units. And then once I do this, remember I crossed out the infinity. Then from E, I'm going to jump to Z. So once I reach E, which is 3 plus 2 plus 4, I'm going to add 2 to get to Z. So I can get to Z by going to 11 units A, B, C, and E. Let's see if that's one option. Or the other option could be, without touching E, another option will be A, B, C to Z, right? Which is going to cost me more because it's 3 plus 2 plus 8, and that's 13. So my better option in this case is, instead of using 13 ABC, I can use 11 A, B, C, E. So it's A to B to C to E to Z, which is 3 plus 2, 5, plus 4, 9, plus 2, 11. That's a better option. The other option automatically will be eliminated. This A to B, which is 3, plus B to C, which is 2, 5, plus C to Z, which is 8, 13, will be eliminated. But notice that we haven't reached F. So we must consider vertex F. How do I go to F? What will be the ideal way of going to F? Remember, we reached D by going through A and B, so that's a 6, right? If I add 2, that's going to be 8. Is this my best option? Yes, it is. So A to B, B to D, D to F, that's 8. And then once I do this, I should be able to circle F as well. So let's go back to the table. You see, notice that E circle is done, but I still have F and Z. I have an idea for Z, but not finalized. And now let's see, I reached out F through A, B, and D, 8 units. And then let's get to the best option to go to Z, which is eliminating 13 ABC and going through ABC E, which is 11. So what is my ideal path to get to Z? My ideal path to get to Z is from A to B to C to E to Z without touching F. This is a total cost of 11, which is, in this case, the shortest path. I hope you find this extremely helpful. Please watch the videos. Unfortunately, the class time does not allow us to go over. That's why I decided to create these videos, use the examples, post these additional lecture notes in Brightspace. Make sure to look at them and reach out if you have any questions. In addition, I posted the solutions of the quiz number 10, which is the final quiz scheduled for this Thursday. Sometime tomorrow evening, the topics of quiz 10 will be posted as well. If I have time, I will do it tonight. Otherwise, tomorrow evening, you will see topics of quiz 10, but you do have the study guide. You also have the solution. So you probably have an exact idea what the expectations are. Trying to remind everyone that the actual quiz is very similar to what you see to the practice quiz number 10. And that's all. This is the final video recording for the semester. Hopefully, the class time will allow us to go over the remaining sections, 8.1, 8.2, 8.3. Have a nice evening, everyone, and I'll see you in class tomorrow.